Hello and welcome to session 198 in the AI Safety Reading Group. Tonight we'll be discussing the first half of the article Language Models Are Few-Shot Learners by Tom B. Brown, Dario Amodei, and many others. This article is published by OpenAI and a number of people who are working there. It is Dario Amodei who has designed and led the research. Tom B. Brown, Benjamin Mann, Nick Ryder, and Melanie Shubha have contributed equally. This normally means that those are the four primary authors, but there are a lot of supporting people. Actually, there are 31 authors in total, so I'll let you go through all their names and backgrounds. I hope that's reasonable. And this is a paper that was published on at the end of May this year. And can be summarized as the fact that scaling up language models greatly improves task-agnostic few-shot performance. And I will be describing the results of this paper, but also please keep in mind that I'm no domain expert in this, so I might from time to time say things that are incorrect. Also, we'll be focusing on section 1 and 2 in this part. So the first background question is natural language processing. What is that? Well, this general subfield of computer science deals with the interaction between humans, the language that humans use, and computers. So there's a part of it which is like low level, like speech recognition and speech synthesis and things like that. But we're mostly talking about the higher level where there are meaning to the words. And in this part of natural language processing, we have things like automatic summarization, dialogue systems, like you can see this gift shop here, machine translation, many other things. And if you go to an even higher level above all these, then there are two major tasks. One is for the computer to understand natural language, and the other one is for the computer to generate natural language. You can actually go even higher. At the very, very highest level, natural language processing is simply predict the next word that a human would say. That would indeed solve all these subtasks if you could do that. But this is generally considered, too high level, or I would. If I should quote myself on my thoughts before I heard about all of this, that would have been that, sure, this predicting in the next word, that's an interesting subtask, but not really relevant, right? Because if you have a task like translating, then obviously you can exploit some of the structure of this problem, right? If you have the problem of translating a text from English to French, then a dictionary that translates words from English to French is obviously going to be really, really relevant, right? So in this way, this the claim that it's just predicting the next word is enough seems really, really counterintuitive. So let's have here is a very, very simple example of this task. I have a pen, I have and then apple, pen, red, or hello. If you have to choose between these, most people would say that apple is probably the correct next word. So what was the state of the art in 2014, according to this paper? Well, I couldn't resist just sniping a bit at Brian Thomas, who in 2014 argued that we are unlikely to see dramatic improvements on this kind of thing through algorithmic insights, because there's not so much precedence for this. And as we'll see, there has indeed been quite a bit. So how would this have been done? In 2014, we would have been using rather simple neural networks, using things like word vectors, where here we have a number of animals, and then some dimensions like, are they domesticated, are they fluffy, and then we assign numbers to those in a word vector. In 2015, things got better. We are using recurrent neural networks with multiple layers that feed back into themselves, and we're using some contextual state. For instance, this is called long short-term memory, where the previous things that have happened are fed into the neural network. Here you can see this box zoomed in. It actually looks like this, and this was quite a breakthrough. This algorithmic progress. Here, according to Wikipedia, this was used really successfully. Now, in 2017, even more progress happened, and this was where Google Brain, which is kind of a competitor to OpenAI, they had a new architecture called the Transformer. The paper is called "Attention is All You Need," and there's a link to it here. And this is what the Transformer looks like. So as you can see, it's a somewhat more complex architecture. There are more links and things that do other things than just the basic neural network. But fundamentally, these are neural networks. So it is basically still a neural network. And the key thing, as you might be able to tell from the title of the paper, is that you can actually do away with all this recurrence and also something called convolutions if you just use the attention concept. So transformers are built exclusively on attention. The good thing about this is when you don't need to feed in the results from just before, then you can do it in parallel. And the fact that the transformer architecture is parallelizable, whereas recurrent neural networks are not, is in fact a very big deal. However, in 2017, this was still something that was used in a task-specific way. In 2018, people started realizing that you could improve this somewhat by having some pre-training done. There were also a number of improvements to the architecture. Throughout this, there are small tweaks and extra features being added to the architecture. So it's incrementally improving, but in aggregate, the architecture is improving a lot. And in this way, the architecture can actually be the same, whether you're doing classification or entailment, similarity, or multiple choice. You actually end up with the same architecture. But unfortunately, in 2018, you still needed task-specific data sets, and you still needed to fine-tune your model against the task at hand. And because you can basically use the same architecture, then this is a substantial step towards making this practical. But the problem is that if we need task-specific datasets, then usually we have only very small datasets. And if you have a really strong model that can model just about anything, and then you have a really narrow training set of training examples, then you are very likely to have your model find correlations that don't actually exist in the real world. Spurious correlations, they call them. So this is a big problem in 2018. In 2019, OpenAI introduced the generative pre-trained transformer 2, the GPT-2, in the paper called "Language Models Are Unsupervised Multitask Learners." In this, they actually dispense with everything that is task-specific, and they compensate for that by using a huge transformer with 1.5 billion parameters. So it's not precisely the same as saying that there are 1.5 billion nodes in the neural network, but you can imagine roughly that order of magnitude. Alec Radwin, in this paper, actually in the abstract, he notes the following: increasing capacity of the language model improved performance in a log linear fashion across tasks. And there is an old rationalist virtue called more DACA, which means that this is the Mosovitz who coined it, that if you have something that appears to be working, then it's not a question of what if you would want to scale it up, but you actually need a really good reason to not scale it up. If it seems like that is something that would work, and that's something, of course, that is in fact counterintuitive to a lot of people, but apparently not to the people who built GPT-2, because they built GPT-3, the generative pre-trained transformer version 3 or -3. So let's talk about that and talk about fine-tuning as well. So what they did is basically they took the same architecture as GPT-2, again with these tiny variations in the architecture that are always being found, and they basically scaled it up, gave it a much larger transformer, a much greater amount of data, both in how many examples and how much diversity, and then they trained it for a lot longer. So that's basically the thing they did. But in this paper, they also explore different settings for how this model can perform. In particular, they have a spectrum on how much fine-tuning or task-specific things to use. So at one end, we have fine-tuning, which is you have a data set that is supervised, where humans have looked into it and said, this is an example of what we want. And this is something you could, in theory, do it with GPT-3. They haven't done it, but I think that would be promising. You can do few-shot learning, where there are you get a few demonstrations, but when you actually need to use it, but you don't change the model itself when you give it a few examples. In GPT-3, they have what is called a context window, how many examples that are possible, and with this size of model, they can have like 10 to 100 examples at most. More than that is out of the attention of the model. And then there's one-shot learning, where there's one demonstration and then also a natural language description of the task. This is often what humans use. And then there's zero-shot, which is just giving a task without any examples. And this is something that a lot of humans struggle with in a lot of contexts. That's of course on the other end of the spectrum. And in the paper, it's claimed that one shot is the fairest comparison to human performance, and that might be true. But I think in general, people don't really care about fairness. I can see it from, of course, a theoretical point of view. That's interesting, but I think in practice, few shot is far more interesting, because if you have the resources to do one shot, then you almost certainly have the resources to do a few demonstrations. So what training dataset did they use on? Recall, or I don't know, maybe not recall, but GPT-2 was trained on 40 gigabytes of data, which is quite a lot. But for this, they used the Common Crawl dataset, which is basically everything that has ever been written on the internet. 1 trillion words, which is 45 terabytes compressed text. They did some filtering on this, so just to pare it down to half a terabyte or something like that. And they are really, cool about this. They just throw out 99% of the data, because there is so much. So if it doesn't, look like a sentence in some primitive way, then they just throw it away, because there is so much data. You might want to compare this to the concept of data overhang, an analogy to hardware overhang from Bostrom's book Superintelligence. This training dataset was certainly sufficient. Even the very largest model in GPT-3 never had to be to use the same sentence 2 times, because there is just so incredibly much data available. One of the things that are different also in the training compared to what is normally done is that they have a larger model that is trained on fewer tokens compared to what is typical in machine learning. There were an interesting bug with obviously one of the few things that you don't want to train this GPT-3 on is the set of solutions to standard tests. Because if you train it on the solutions to the standard text, then it might just look that up, and that's of course cheating. So they tried to avoid that, but actually they failed a bit, and there's a discussion about how they tried to get around this. It cost quite a bit to train this model, so they couldn't just repeat it. But this training was provided by Microsoft, who I believe is a pretty major sponsor of OpenAI. So how did they do the evaluation? Well, they took an K, which is like a number like required, depending on how much is required for the test for conditioning, and because they did this on a huge amount of different tests, then the way they did this evaluation actually has a lot of variations and details. In some case, for some of these benchmarks, then the actual results are not available as something you can download. You can only query a server through a web service to figure out what is my generation actually correct. So the model that is called GPT-3 has a number of parameters, well, hyperparameters, with how large is the neural network, how many layers, and there were these attention heads, etc. And these are the hyperparameters that are being used. And one of the things that they note is that these numbers down here actually don't matter very much. Of course, the number of parameters matter, but it's not really strongly sensitive to how many heads you have, etc. I think that's interesting, because I'm both interested in the things that matter and the things that don't matter. And it appears obviously that having a huge amount of compute matters a lot. The transformer architecture matters a lot. Things like incremental tuning and things. The fact that this doesn't matter, I actually also find it quite interesting. Now let's talk a bit about how GPT-3 learns. And they're using something called that the authors called meta learning, which is where the model develops, it learns how to learn, have a set of skills and patterns that it has at training time, and then it uses these when it's time for the test for inference to either directly recognize the task or adapt to that. So the way this works during training here is there is an outer loop and an inner loop. So on the outer loop, it's using rather standard stochastic gradient descent in this pre-training. And then in the inner loop, it is learning things in specific contexts, like additions or flipping letters or translations and things like that. And in these, while it is learning, it gets results that are really, really poor compared to something that is fine-tuned. But it does this a lot, and it learns a huge amount of these skills that it will later be able to put into use. So let's see for the actual result here. Now this is the accuracy on a large number of benchmarks, some standard and not so standard benchmarks for how good is this model at doing things that humans can do. And as we can see, there are a lot of things that and down here we have the size of the neural network, basically the number of parameters. And as you can see, there is a trend going upwards, both with zero-shot learning, one-shot learning, and few-shot learning. It does seem to somewhat increase, and on aggregate, whenever you increase the size of the model, you get a substantial performance improvement. And In particular, one of the things you can directly measure from all this is what they call log loss, and this is something that's used in machine learning, and this is a measure for how good your predictions are. And according to this log loss, your performance increases quite linearly with how good your guesses are. So let me just quickly give a hint of what log loss is. Like if you have an algorithm that assigns probability 1, that is 100% certain of something that turns out to be the truth, then you want a loss that should be 0 in order to train your algorithm. And if you assign really low probability to something that is the truth, like 0.01 or something like that, then you want a huge loss. And the mathematical function that satisfies this is the negative log of probability. In the article, they call it just log loss. They mean the negative log, of course, but yeah. So this is how it looks when you scale up to 13 billion parameters. How about in G3 when you scale up to 175 billion parameters? Well, you get this. And this is pretty broad improvements on basically all the tasks. One of the things that I noted in particular is just how many of the tasks that just go, a number of them go straight up to 100%. So it means that I haven't looked into which does this, but apparently a number of tasks just have human level performance. And you know, there seem to be a lot of things where the tasks were basically impossible to solve at 13 billion parameters, and you know, some of them go really far up that seem to be, you know, not solved, but really improvements are made by going from 13 to 175. This might not be that unexpected, because the learning that you do in pre-training involves a lot of very varied skills, and the more things you have to put into the model, the more difficult it becomes. But if the model is larger, it can contain more skills, and that's why you should kind of expect that this kind of meta learning is something that improves dramatically with scale. So let's go into one particular line from this, from one particular test, which is removing extra characters. So let's see that task in particular. You have a word like succession here, and then you add on every other spot you add a random character, and then you will see if the AI is capable of filtering that out. And here you can see that basically with 1.3 parameters, it basically can't figure it out. It gets slightly better if it has some more examples. 10 examples here, 1 example here. And you can see with 175 billion parameters, it just performs really well, even without a prompt. Even if it's just given the word succession, then it can indeed figure out the next word should be succession, which is, you know, kind of impressive. So in this example, Dario Amadei admits that this is a particular striking one, but it is a representative of a general trend. I feel this is not one of the a really good example for talking about natural language processing, in that this is something where you could, you know, just removing every other character is something that could be done by a really simple program, and this specific task of removing every other language is something that is so simple that it might you might expect it to be contained into the model at some point, so that it would just be able to, you know, solve it to 100% every time. So what is the conclusion from all this? Well, on all these tasks we get some really promising results. sometimes even competitive with the state of the art by fine-tuning. So this is some really impressive results. And it seems indeed that the more the larger the model is, the greater the difference between 0, 1, and few shot performance is. So this could be argued to mean that when the model is larger, it has better meta learning. They're not really willing to strongly conclude this, but I think this this gives a fairly good indication that this might be true. And indeed, the title of the paper, that language models are few-shot learners, is also hinting of a very general conclusion. So, one of the things that I think would be interesting to discuss is last week or 2 weeks ago we saw Ben Garfinkel say the following: that if an AI has the capability of understanding natural language, it will be using this understanding for the interpretation of its goal. And if we look at GPT-3, then this is an example where at one level it's obviously false, because GPT-3 has precisely the goal of predicting the next word. It doesn't use common sense in figuring out if this should be its goal. It just has this goal, but it has common sense. I would even call it a moderately rich model of human cognition, because this is something that can be used for predicting what the next word that a human would use. And I think this is an interesting. We will probably get more clarity on this question in the rest of the paper. And another thing that I also couldn't stop thinking about is that if you have something that has a really rich model of human cognition, like GPT-3 can understand if sentiments like that a human is angry or sad, or that this text is written by a sad person or something like that. And if you have something that understands sentiments really, really well, then you have the feeling that, well, it might not just understand what sadness means, but actually be able to feel sadness. I think that's unlikely, but I am not really 100% confident in this, and I'm not really sure how you can have 100% confidence in that conclusion. But I expect a lot of people will disagree with that. That is all for today. Thank you, and see you next week.